Hello, physical science students, and today is the last section in our unit on work and energy. We are going to look at something called thermodynamics. Great big exciting sounding word, and within the definition of what thermodynamics is, we're going to look at what systems versus surrounding is, how energy, work, and heat are related. We're also going to look at the first and second laws of thermodynamics. What are they? What do they mean? And we're going to look at some applications for all of this. We're going to look at heat engines, internal combustion engines, refrigerators, conditioners, heat pumps. So if you ever wanted to know why and how these things work, hopefully we can answer a few of those questions for you today. Thermodynamics. The definition of thermodynamics, it is the study of the relationships between thermal energy, heat, and work. Pretty simple. How are they related? How are energy, heat, and work related? Well, to answer this question, it's actually a very complicated question. We're going to try to simplify it, but to start to answer it, let's look at an idea where we have what is called a system versus a surroundings. Remember, a system is just something that I can put a boundary around. So here I have a system. It has a boundary around it. The surroundings are simply everything else. If I were to describe this in terms of system versus surroundings, the system would be this the combustion happening, the combustion of the fire, the combustion of the wood, of the fuel. The surroundings would be this area around it. I can get more specific. I could say the surroundings would be the rest of the universe, or simply the rest of the earth, or this area within the park, or wherever I am. In order to understand the dynamics between systems and surroundings, I need to define a few, just a few ideas for you. You do not need to have this memorized, but this was just to try and explain these ideas to you. Whenever we have a triangle like that, it means change in. In this system, Q is going to represent heat. In thermodynamics, Q is generally used for that, and W with a little w is representing work. When I have a system and I have my surroundings around it, if I can put energy into my system, that means energy is coming out of the surroundings and going into the system. I can also have my system putting energy can leave my system and go into my surroundings. The case of fire, where we have this combustion happening, we have fire as our system, thermal energy is being transferred from the system to the surroundings. And you know that because when you're standing in the surroundings, you feel the heat from the fire. Now remember, just to review, energy is the ability to cause change. We have over here work, because work transfers energy. Well, what about heat? Over here, we have energy as heat also. We can have energy leaving the system and going into the surroundings, or energy coming from the surroundings into the system as heat. So work and heat can both exit and enter the system in the form of energy. It's important to keep in mind we have two different kinds of systems. We can have what we just described where energy can enter the system or exit the system. We can also have, that's called a non-isolated system. We can also have an isolated system where no energy transfers take place at all. That would not obviously be the case with our fire, but we can have a system where energy transfers, the barriers around the system are such that no energy transfers can take place. That's called an isolated system. So we're going to look at the first law of thermodynamics. It's really little bit more complicated than this. I'm going to try and simplify it and tell you just what you need to know about it. But the idea is that the heat transferred into the system plus the work done on this system is going to equal the increase in the thermal energy of that system. That's essentially the idea. And what you need to understand is, because of that, there are basically two ways that you could increase the temperature of a system. You could heat it, add heat to the system, or do work on it. So transferring heat into the system, heating it, or doing work on a system will increase the temperature of a system. It will increase the thermal energy of a system. Now that you have a little flavor for the first law of thermodynamics, we're going to look at the second one, and there are only two. The second law of thermodynamics has to do with the idea of entropy. And you may or may not have heard of this word before, but I'm going to back up and explain it. We all know that energy spontaneously spreads from regions of higher concentration to regions of lower concentration. You know that because this man is sitting in front of this heater, and the energy is spontaneously spreading from this heater where there's high energy concentration into throughout this room where this man is sitting to areas of lower concentration. You do not see the little bits of energy that are about this room, this kind of cold room, that are coming into this heater. The little bits of energy in this room are not transferring into, they are not spreading into this heater. You would never see that happening. So because of this second law of thermodynamics, we know that energy moves from regions of higher concentration to regions of lower concentration. So let's look at some applications of these laws of thermodynamics and these ideas we've been talking about. A heat engine. What is a heat engine and how does it work? That's a really, really good example because we're all really familiar with the internal combustion engine, which is a type of heat engine. A heat engine simply converts some thermal energy into mechanical energy. A car engine is a type of heat engine. It's a specific type, an internal combustion engine. An internal combustion engine is a heat engine that burns fuel inside a set of cylinders. Here is a diagram illustrating how a four-stroke cycle in an automobile would work and what that means. Basically, these set of cylinders function in these four steps. First, there is an intake of air and fuel. This happens as the piston moves downward and draws the air and the fuel mixture into that cylinder. The second step is a compression step. The piston is moving upward and compressing the air and fuel in a smaller volume. In this third step, we actually have right here a spark plug igniting this fuel-air mixture and creating a small explosion, which forces the piston down. And then that brings us to the fourth step, the exhaust step. As the piston moves back up, the exhaust valve opens and then the hot gases are pushed out of the cylinder. So let's talk a little bit about the efficiency of these heat engines. And everyone knows probably that car engines are notoriously not very efficient. In fact, 3/4 of the chemical energy is never even converted into mechanical energy. Some of the reason is friction, and we've talked about that before. Remember, a lot of inefficiency is due to friction. But even if there was no friction whatsoever, we still could not have a 100% efficient heat engine. And that has to do with the fact that the difference in temperature between the burning gases and the air has a lot to do with the efficiency. We can increase efficiency if we were to be able to somehow raise the temperature of the burning gases and decrease the temperature of the surroundings by a lot. That would end up increasing the efficiency. That's not really very easy or practical. So efficiency of heat engines is quite low. Let's look at another example of thermodynamics at work in everyday life, and we all appreciate our refrigerators. Keeps our food cold, and how do those work? Well, let's take a look at this little diagram. First of all, there is coolant, a liquid coolant that goes through an expansion valve in your refrigerator and is converted into a gas, and it expands into this gas where it's pushed and flowing through these pipes in your refrigerator. This coolant, essentially, as it's going through your refrigerator, receives thermal energy from the inside of your refrigerator. Thermal energy is transferred into that coolant as it's flowing through those pipes. So that's what cools your food. It takes the thermal energy away from the inside of the refrigerator. As that gas flows through this pipe, it is pumped into by a compressor pump. And as this gas is compressed, it actually ends up becoming warmer than the room, where it is pumped out through all of these coils back on the back of your refrigerator. That's where those are usually located. And the thermal energy then can spread out throughout all of those coils back into the room. If you ever buy a refrigerator, you can feel that thermal energy emanating off of those coils somewhere on your refrigerator. And that is essentially how your refrigerator works. So how do air conditioners work? Well, we don't use those too often up here, but it basically operates like a refrigerator, except that the warm air from the room or from the inside of your car, if you're doing your air conditioner in the car, is forced to pass over the tubes that contain the coolant in the air conditioning system, and then thermal energy is transferred from the warm air into the coolant, and then the thermal energy that's absorbed by the coolant is transferred to the air outdoors. And you probably know this if you've ever stood by an air conditioner unit outside of a big building. It's giving off quite a lot of thermal energy. So quick review. What's thermodynamics? Remember the study of what? What are systems versus surroundings? How do we think about that? What is the relationship between energy, work, and heat? What's the first law of thermodynamics? Remember, you just need to know what are the two ways to increase temperature. What are isolated versus non-isolated systems? What's the second law of thermodynamics? What are heat engines? What's an internal combustion engine? How does it work? How do we think of the efficiency of heat engines, and what is it? Not necessarily a number, but how efficient are they? How do refrigerators and air conditioners work? Here are some advanced ideas for those of you looking to get a 4 or come up with your own questions, your own ideas, your own investigations, and come in and show me. I look forward to seeing you in class.